All right, in this section 8.2, we're going to be talking about fluid pressure and fluid force ultimately is what we're going to be interested in. We're just using pressure as a way to get there. So fluid force is the fluid pressure times the area. So if we have something that is submerged under a fluid, so let's go ahead and say the surface of water is right here, or any fluid, doesn't matter, something, even air for that matter. Um, and then let's say underneath of it we've got this plate. Now this plate, I'm going to draw it with perspective so that it looks like it is the surface of this right here is parallel to the surface of the water. So it's not like it's being dipped into the water this way. So all of the water is directly kind of on this entire area. So whatever this area is, so whatever that area is, the fluid force would be the fluid pressure. So the pressure that is felt at this depth. So let's calculate that. So I'm going to go ahead and do a little measurement thing here. And let's say this is submerged some depth h below the surface of the fluid. So a depth of h. So then the fluid pressure, P, from above in definition 1 is going to be the density, rho, of the fluid times the acceleration due to gravity, so 9.8 meters per second squared, times the depth. Because we know that the deeper you go, we've all been in a pool or something, and we've swam and we've gone underwater, and we felt that the deeper that we go, we feel, sometimes pain in our ears or our head, and that is our sensitivity to that pressure. Because the deeper we go, you can think of there as being more of the fluid on top of you. And if there's more of something, that thing has a density, so therefore there is a certain mass associated to it. And then, just like everything on Earth, and all mass, it's subject to the gravitational force. So all that water above you is pushing inward upon you due to the fact that it has mass, and therefore gravity pulls on it. So that tells us the pressure. Now, pressure, from a physical point of view, pressure has units of pascals, which is really, if we think of it in terms of other SI units, this would be a Newton per meter squared. So really, pressure is force divided by area. It's force per unit area. Here in America, we use PSI, pounds per square inch, but again, a pound is just the imperial unit for force, and then a square inch, of course, is area. So pressure is force times area. So now that we know what the pressure is, if we want to know the fluid force, then if we think about it, if pressure is force divided by area, then fluid force should just be pressure times area. And that's exactly what we're going to do. We're going to do the pressure. So let's do fluid pressure. Oops. Times the area on which that pressure is acting. So really, the interesting thing happens when you have some sort of object or shape or solid or something that is not at a constant depth. So I drew this plate specifically to be parallel to the surface of the water so that every single point on the surface of this plate is at the same depth. So that the calculation for the fluid force acting over this entire plate is very simple. We just calculate the single pressure, because there is only one pressure because all of these points are at the same depth. So the pressure is equal over the entire plate, and then we just calculate the area of that plate and multiply them. But if our plate were, for instance, maybe tilted, I don't know how to draw this, or maybe let's say I have some sort of let's say I've got a sphere submerged underwater. Well, then the pressure at the very top is different than it is right here and right here. Okay. So we're going to take a look at shapes and solids or plates that are oriented in such a way that they are the pressure varies continuously over that surface area, in which case we would need an integral in order to calculate the pressure. But before we go there, let's take a look at example 1, just a more concrete example. So suppose we have a 2 by 2 by 5 box, so 2 meters by 2 meters by 5 meters. So let's think of this as having a square base, and then we've got 5 meters for the height. So there's our 2 by 2, 2 meter by 2 meter by 5 meter box. And we're told that this box is, let's see here, 3 meters beneath the surface. So here's the water. We are told that the fluid is water. So calculate the fluid force acting on both the top of the box and the bottom of the box. So first thing I'm going to do here is just label the fact that this distance here is 3 meters. So we really have the same area, right? The top of the box and the bottom of the box, they have the same exact area. So the area here, area of the top is equal to the area of the bottom, which is 4 square meters. What is going to be different, though, is the pressure, because down here, all the way down here, we are at a depth of, well, it would have to be 3 plus 5 meters, so 8 meters of depth. So the pressure, P, at the top of the box is going to be the density of the fluid, rho, times the acceleration due to gravity, g, times the depth, which for the top is going to be 3 meters. And really quickly here as a reminder, g is 9.8 meters per second squared. And if your fluid is water, so for water, the density, rho, is 1,000 kilograms per cubic meter. All right, so the pressure for the bottom is going to be a lot higher. Rho and g are going to stay the same, but this depth is now 8 meters. So together with the two areas and our two pressures, we can calculate that the force of fluid on the top of the box is going to be 4 times our pressure. So that will be 12 rho g, and this would be units of newtons, so N. And the force acting on the bottom of the box is 8 times 4, so 32. 32 rho g. Newtons. For many problems, especially anything that's handwritten, we're going to be fine with you leaving your answers as in terms of rho and g. You don't have to actually plug in what rho is. It's easier, it's less work, just do it that way. On online homework or anything you're typing into a computer, you may very well be required to do that. But either way, I would solve the problem leaving things just written in terms of rho and g, and then if you do have to type your answer in, only when it comes time to type in your answer should you replace rho with 1,000 in this case, and g with 9.8. Okay, and that's it for this problem.